In the pit lane of a 2025 Grand Prix, every surface is a product of computational fluid dynamics and specialized composite engineering. But as the carbon fiber dissolves into hardwood, the engineering lineage becomes visible. We generally view the history of terrestrial speed as a linear climb, assuming that the mastery of complex physics is a strictly modern development. The challenges of managing asymmetric aerodynamic loads, dampening high-frequency ground vibrations, and balancing the flexing of structural components appear to be problems solved only within the last century. In reality, these specific mechanics were reverse-engineered over 3 millennia ago. Through the construction of the Tutankhamun-class light chariot, ancient engineers developed the foundational dynamics required for high-performance racing. Early wheeled vehicles in Mesopotamia were built for torque rather than speed. These heavy carts utilized solid wood disc wheels on fixed axles, creating massive unsprung weight and high rolling friction that kept speeds to a slow, ox-pulled crawl. The shift occurred when the Egyptian military reduced vehicle mass to its absolute limit. By utilizing heat-bent wood for a 6-spoke wheel, they created a 30-kilogram racing vehicle capable of reaching 40 kilometers per hour. At 40 kilometers per hour, the chariot encountered a new physical barrier. Airflow became dominated by inertia, meaning the aerodynamic drag resisting the vehicle's forward motion began to increase quadratically with its speed. This simulation shows a rotating spoked wheel's complex wake. The top moves at twice the vehicle's speed, while the bottom has zero relative velocity, causing chaotic flow separation. Spinning traps stagnant air, lowering drag, but drastically increases the energy needed to push the spokes. The ancient 6-spoke design was a compromise between these two forces. It provided enough aerodynamic transparency to minimize rotational resistance while maintaining the structural integrity needed to survive high speeds. High-speed aerodynamics are ineffective if the vehicle vibrates apart over rough terrain. Without the metal coiled springs or hydraulic dampers of a modern race car, ancient engineers had to find another way to manage impact energy. The solution was the rear axle layout. By shifting the axle to the back of the cockpit, they turned the long hardwood draft pole into a massive leaf spring that bent downward to accumulate kinetic energy when the vehicle hit a bump. To prevent that energy from violently releasing and bouncing the passengers, the chariot floor was made of interwoven rawhide leather. As the dynamic load pushed down, the leather strips rubbed against each other, dissipating the energy as heat through micromechanical friction. This organic damping coefficient reduced vertical oscillations by nearly 2/3, providing the stability required for an archer to fire at full speed. By the Roman era, chariots were specialized racing machines optimized for the Circus Maximus. Because these races only turned counterclockwise, the vehicles were subjected to continuous, unbalanced physical forces. Centrifugal force transferred massive lateral stress exclusively onto the right wheel during every turn. To prevent fatal spoke failures, Roman engineers heat shrunk an iron tire onto only the right wheel. This prevented shattering without adding useless weight to the largely unweighted left side. This strategy of localized reinforcement anticipated the same asymmetric load challenges modern railway engineers face today when managing uneven wear on wheels navigating constant curves. In the 2024 and 2025 Formula One seasons, a similar focus on structural deformation became the center of a major regulatory controversy. Teams began engineering flexi-wings designed to circumvent aerodynamic drag limits. This is known as aeroelasticity, the intentional design of components to bend organically under aerodynamic pressure. By flexing backward at high speeds, these wings shed massive amounts of drag. The FIA responded with Technical Directive 018, tightening the static load tests. They reduced the allowed deflection from 15 millimeters to 10, forcing teams to move toward more rigid structural designs. The mechanical parallel is direct. Whether it is a carbon fiber flap flexing on a modern straight or a wooden draft pole bending under the payload of an Egyptian chariot, both rely on the same principle of intentional structural deformation to manage dynamic loads. In both eras, engineers independently discovered that allowing a machine to bend is often the most effective way to keep it from breaking. The ancient methodology of optimization was based on physical trial and error. Today, aerospace and racing development has moved entirely into the virtual domain. This visualization shows meta-model-based design optimization. Modern engineers use mathematical surrogate models as stand-ins for real-world physics, bypassing decades of physical testing. Within this virtual environment, supercomputers predict how an airfoil or spoked wheel behaves across thousands of microvariations. The chariot builders of the Bronze Age arrived at the same physical conclusions we now reach through digital simulation. They identified the balance between aerodynamics, weight reduction, and structural integrity that continues to define the physics of high-performance vehicles.